11, part 3. So in this part, we are going to talk about another unsupervised learning algorithm called k-means clustering, not to be confused with the k-nearest neighbor algorithm, although they share the same initial letter k. But well, if you want 3 clusters, then it's called 3-means clustering, so they are not really the same. But well, in any case, they are completely different algorithms. So let's talk about k-means. So k-means is another very simple clustering algorithm, just like hierarchical clustering. So the idea is we start with random cluster centers, and we assign the points that are the closest to these cluster centers, and then we update the cluster centers based on those points that are assigned to that cluster, and we repeat this process until it converges. So in the actual lecture, we'll go through some numerical examples. Here, I'll just show you a diagram. And instead of me drawing lots of points, let's use an online demo. So here, suppose there are 3 clusters and a lot of points. Actually, the computer cannot see that there are 3 clusters. So to the computer, it's just a bunch of points. And the computer needs to figure out which points are closer to each other and put them into a group or a cluster, and that's basically what we're doing here. So let's start with a random cluster center like this, maybe say another one, and maybe let's put another one here. So the first step is to find all the points that are closest to each cluster center. So for example here, these points are actually closer to the green center compared to the red and blue center, so they are assigned the color blue. The color green. And similar for these points, they are closest to the red center. It seems it's incorrect now, but the next step is we're going to actually find the center of all of these points, and then we can update the center. So for example, the green points will move to somewhere in between, and the red center will move to somewhere in between these two groups of red points. So let's actually do it. Okay. So now both of these moved, and let's reassign them. So these ones are still red, and there is still a part of this cluster that belongs to the green cluster. Let's do it again. Red will get closer, and now the red center seems to be occupying this region, and if we update again, all of these will be labeled red. Okay, so let's do it again. Recenter. So only these are green now. So if you recenter, the green center will go back, and it seems stable now. Let's try again. Okay, nothing changes. Let's try again. Nothing changes. So now it's stable. So it converges. And the 3 clusters are correct. They are actually the 3 clusters that we want. But let's try again. Maybe with different cluster centers. Maybe let's say just put all of them here, and let's say go. And at the beginning, it seems already is correct. So you can guess probably the red point will move to the actual center, and the green point will move to the center. And indeed it is. So in 2 steps, it converges. So basically, it doesn't matter where you start. It seems we are always converging to these 3 big clusters. The reason is because this data set has a really clear cluster structure. But if we start with something that does not have a good cluster structure like this, it's not clear how many clusters are there. There seems to be 2 for the eyes and 1 for the mouse, but otherwise it's a circle, so it's like a cluster everywhere. So let's actually try this. So let's try to add many cluster centers. Okay, so if we start from something like this, and at the moment it's completely not correct, but let's keep updating them and see if we reach some point that's stable. So here it seems to be stabling. Let me use the mouse instead of the pen. Okay, so here it seems it's kind of stable now, and there are some still small movement, but it seems that we have one cluster for each eye and one large cluster for the mouth. So it seems to be something that's reasonable, but as I said, there's no clear cluster structure, so it's hard to evaluate whether it's a good clustering or not. In any case, let's get back to the slides. So the next thing we want to do is obviously talk about the mathematics and some properties of this algorithm. So most likely unnecessarily complicated stuff, but we'll go through them anyways. So here, first, let's define what a cluster center is. So the definition is the intuitive one. So you just sum up the points in the cluster, and then divide it by the number of points that belongs to the cluster. So it's just the average. And given the average, given the centers, we can define distortion. So distortion is basically the total distance from the points to their cluster centers. So the first thing is we need to define what is their cluster center. So we find the cluster center among the k possible centers. We find the one that's closest, that has the smallest distance to our point here, and we assign that point to that particular cluster and call it k star. And then we compute the distance between that point and that cluster center. And we add up the distance over all points in the training set. And that result is the total distortion. So it seems what we're doing is we are trying to minimize total distortion, and by some kind of iterative algorithm, so it looks like gradient descent, and it indeed is gradient descent. But before that, let's first talk about some properties. So first, it stops in finite steps. So good that it always stops. But the problem is when it stops, it does not necessarily reach the global minimum. So the reason is the function is not convex. So remember at the beginning, if we have a convex function, then we use some kind of gradient descent, it will always converge to the global minimum. But if we have something that's like not convex, then maybe we will converge here, or maybe we actually converge to the global minimum. So it is this case here that the objective is not convex. So that's why sometimes we would fail and we would not be able to reach the best cluster. But let's actually go back and see why it is not convex. So if we use the distance function as the square of the norm, then it's actually a sum of squares. So that part seems to be convex. So the part that's not convex is actually the arcmean part. So the arcmean part is obviously not convex. It's basically like taking the minimum distance between x and all the cluster centers. So this expression basically looks like taking the minimum of x with all the k centers, and each of this is a sum of square, which is convex, but the fact that we're taking the minimum make it not convex, and that's why a iterative algorithm like gradient descent might converge to some local minimum instead of the global minimum. Let's actually talk about a counterexample. I will try to show you with this demo. Let's try this and see if we start with a point here, and maybe another point in the middle. Hopefully this works. And if we try to keep updating, let's try. Okay, so I think I click update and reassign many times, and it stays like this. So basically, this one small cluster is split into two, but these two large clusters are combining to one larger cluster. So, and it converges. So it's kind of a local minimum here. The global minimum is obviously the one you saw. It's that there are three clusters, one for each obvious cluster. But here it's not doing the job because it's converging to some local minimum. So that's the possible problem. Like we have the same problem with training neural network with gradient descent. So the only way to fix this is to just have random restart. So basically start with different initial points. So if you don't choose this particular one that I picked here, then most likely, as I showed you before, most likely will converge quickly to the three clusters. So what you can do is basically you can start with different cluster centers, random cluster centers, and just pick the one at the end with the lowest total distortion. So that's basically what you should do. And let's get back to see why it is gradient descent. So the objective is this thing here, and if you take the derivative, I think I'm missing a square here. If you take the derivative, you'll have a 2 in front, and then the sum, set it equal to 0. Basically, set the derivative equal to 0, and then you can solve that expression. That expression will characterize our local minimum. So here, if you look at this is just the definition of cluster center. Right? So it's the cluster center is just the average of the points in the cluster. So this is exactly our k-means algorithm step. So it turns out it's similar to our gradient descent. So as I said, it might converge to a local minimum, and that's a problem with the k-means algorithm. Okay, and that's basically all I want to talk about k-means clustering. Here is another summary of what just happened with these mathematical notations. And there is the same problem with what happened with hierarchical clustering, which is we need to figure out the number of clusters. So of course, the first way I will state is using prior knowledge. So suppose we know that there are like 4 clusters, or we want there to be 4 clusters, then we can just set k is 4. There is another tempting idea. Basically, we can choose a k that minimizes the total distortion because we are fixing a k and minimize the distortion anyways, right? It turns out it's not working because as k goes larger, as we have more clusters, then obviously the total distortion of these clusters will go to 0, right? So if you look at each point being a cluster, then the total distortion will be exactly 0. And in fact, as I said, the more cluster, the less the total distortion. So it's not a good idea to pick k this way because we'll usually pick a large k. However, what we can do is actually kind of add a penalty or cost to having a large number of clusters, and we used to call these the regularizers, and here we'll do it again. So we'll have a regularizing constant, we'll call it lambda again. So it basically is the trade-off between smaller distortion and large number of clusters. And we also multiply by some constant. So m here is the number of dimensions of the x, so number of features basically. And log n, this n, is the number of training examples. And we just figure out the k that minimizes both the distortion and with a penalty on large number of clusters. So if we find such a k, if we choose our lambda properly, so I don't really know what properly means, but again, we need some prior knowledge to choose this lambda, and then we can find our optimal number of clusters. So that's one problem. And another problem that did not happen with hierarchical clustering because we did not need to randomly start anywhere. Here, we do need to randomly start, so there are ways to choose good random starting points. So the first one is just what I described before, just completely random, just pick points. And another perhaps better algorithm is you can start with one random point. So let's suppose there are 3 clusters again. Let's pick just one point, say here. Then the next thing you can do is you can pick the point, all the points, among all of them, the one that's furthest from this point. So maybe I think it's one here. And then next, you pick another cluster center that's far from these two. So there is a problem of defining what do I mean by the furthest from 2 points. But what you can do is similar to the single linkage and complete linkage. You can just pick the one that's the furthest from the closer of 1 and 2. So for example, so something like this. So it depends on how accurate you want them to be. You can do whatever you want. You can just pick a point that's far from both of them in terms of the sum of the distances or whatever you like, basically. So after you pick these 3, then obviously in one step it will converge to these 3 cluster centers. So the convergence will be a lot faster compared to if you pick all the points randomly. Okay, that's actually all I want to talk about k-means clustering. Again, it's a very simple algorithm, and mathematics is simple as well. So I will talk about one possible improvement by making the cluster membership kind of random. So in k-means, each instance belongs to one of the clusters. But if we want each instance to belong to multiple clusters at the same time, with different probabilities, then we can get a kind of continuous or probabilistic version of k-means. And that's called the Gaussian mixture model with k Gaussian clusters. And the way to train this is expectation maximization. So remember in the hidden Markov model lecture, we talked about EM algorithm already to deal with missing data. And here we are basically dealing with the missing data. The missing one is the labels. So we are going to use EM algorithm again. And let's look at the details. So first, we're going to start with random cluster centers, and also we need random cluster variances. So variances basically is the cluster size, and the means are basically the cluster centers. So if you look at this algorithm, it's actually the same as k-means. It's just probabilistic. We have more variables. So we also need another variable called mixing probability, which is what percentage of the point belongs to each cluster. So we need to estimate that as well. So we start with basically random centers, and then we assign the points to these centers the same way. And the way we assign them is just use this frequency or this probability. So here, the probability that the x belongs to each one of the cluster is given by this Gaussian distribution density thing. So if you have taken Stackhouse, you are familiar with this. If not, you can just view this as a way to compute what's the probability that a point belongs to a cluster, or basically it's kind of a distance measure between a point and a cluster, a Gaussian cluster, and then you use that probability and divide it by the total probability that it belongs to all the other clusters. So it's basically a fraction here, and this represents the probability that your xi belongs to cluster k. And we're calling them the responsibilities. They are, again, just the probability that our instance I belongs to our cluster K. And then basically we're given the labels. Now we just recenter. So this is the recenter step. So again, we are calculating the center using some formula that's like taking the average and divided by the total number. but here this average is the weighted average. So again, this is computing the center again. We're going to compute the size again. So this is the standard variance formula. So it's a square of each instance, the difference between each instance and the center. And then we are weighting them by the probabilities again. So we basically update the cluster size. And at the end, we update this mixing probability as well. And we're going to do this, we're going to repeat this until it converges. So again, the idea is the same as k-means, it's just the formulas is more complicated and we are using probabilistic assignments instead of assigning each point exactly to one of the clusters. So let's see one other online demo. So say here, a cluster would look like this. So the mean is basically the center of these ellipses, and the size is kind of the radius. So what I mean by size is the variance. So you have basically two variances in each direction, and there is actually a covariance, but we'll not talk about these details. Let me actually put another cluster around here and see if it works. So let's start with 3 clusters. Now the third cluster is completely wrong, but let's try to update it. Okay, the first update is already good. Second, third, well, it's actually great. So after a few updates, it's already working. So let's actually try one that maybe is closer here to see if it works. Let's try 4 clusters. Now this one is completely wrong, and let's try to update it. And it actually works great, right? So all of them converge to the clusters that we wanted. And note that the difference between this and the actual k-means is that the cluster size can be different. So if we use k-means, then you notice that each cluster must have the same size, or some of the points in the other cluster will belong to that cluster. So here it does have the advantage that we allow different sized clusters, and it converges. The algorithm basically works the same way.